Hello friends, so welcome to the third lecture of this module, and in this lecture we will continue from the last lecture in which we have introduced Euler's method, and in the Euler's method we have seen that we need to reduce the step size for getting a better accuracy, and hence reducing the step size means you need to do more calculations. So, in this lecture our aim is to develop a whole family of numerical methods that can attain any order of accuracy, unlike the Euler's method where we are having accuracy of order h. So, here we will do the Taylor's method in this lecture, and specifically I will talk about quadratic Taylor method, and then I will tell you how we can generalize Taylor method up to any order of any order. But in Taylor's method we need to know how to determine higher order derivatives of the solution of a differential equation at a point, and this is also we will explore in this lecture, that how to calculate higher order derivative for a given function. So, let us start with quadratic Taylor method. So, the quadratic Taylor method is based on a more accurate approximation, that is the approximation up to second order derivative. Like in Euler's method we have taken only up to first order derivative, but here we are taking up to second order derivative. So, a function f can be approximated about a point x naught by this expression, that is f of x naught plus h times f prime x naught plus h square upon 2 f double prime x naught. To describe the algorithm we need to specify how the numerical solution can be advanced from a point xk yk to a new point xk plus 1 yk plus 1, where xk plus 1 is xk plus h. The basic idea is to use the above equation and compute yk plus 1. So, by the Taylor series expansion we can write yk plus 1 as yk plus h time y prime k plus h square by 2 y double prime k. So, in this expression you can see we are having y prime k as well as y double prime k. So, y prime k can be given by the differential equation from our initial value problem. However, we need to calculate y double prime k here. So, for calculating y double prime k we will use this lemma, and in this lemma we are having that if a function y prime that is equals to f of x y, that is the given differential equation with initial condition y at x naught equals to y naught, and the same time suppose that the derivative of f of order p minus 1 exists at the point x naught y naught, then the pth order derivative of the solution yx at x equals to x naught can be expressed in terms of fp capital F p x naught y naught, where capital F p is a function defined by f and its derivative of order less than p. So, let us take an example to get a better understanding of this lemma. So, in this example we are having a differential equation y prime equals to x plus y square together with initial condition y at x naught equals to y naught. Now, let us assume that y prime equals to f of x y, or I will write f1 of x y. Now, if I calculate y double prime, that is some according to previous lemma I am having f2 of x y, then this is the differentiation of this particular term with respect to x. So, it will be 1 for this particular x and then 2y into y prime. So, that is 1 plus 2 times y, and y prime is f1 of x y. So, here you can note down for calculating the second order derivative of y, that is the y double prime, we need the value, that is the value of y as well as value of capital F1 x y, that is the derivative of y which is less than order 2. and this is coming out now. If I substitute the value of f1 xy from here, that is your x plus y square. So, it will be 1 plus 2xy plus 2 times y cube. Similarly, we can calculate higher order derivative. For example, if I want to calculate y triple prime, that will be f3 xy. So, it will become 0 plus 2 times y plus twice x y into y prime plus 6 y square into y prime, or from here I can write, if I want to calculate from here directly, 0 plus 2 times y into y double prime. So, if I am coming from here, so it will be 0 plus 2 times y into y double prime plus 2 y prime whole square. So, basically it is 2 times y into f2 xy plus 2 times f1 xy whole square. So, here again you can note that I am using the value of y, I am using capital F1, I am using capital F2 for calculating capital F3 according to previous lemma, and by substituting all these values I can get y triple prime. Now, how to use quadratic Taylor method? For that again we will consider an example of an initial value problem that is given as y prime equals to small f of xy, that is also my capital F1 of xy, and it is given as x minus 1 over 1 plus y, and the initial condition is y at x equals to 0 equals to 1. We want to solve this particular initial value problem on the interval 0 to 1 with step size h equals to 0.5 using quadratic Taylor method. So, first of all we need to calculate the second order derivative of y for applying the quadratic Taylor method, and for doing that y double prime x can be given as f2 of xy, that is basically 1 plus y prime x upon 1 plus y whole square. So, now after that what I will do? I need to solve a differential equation y prime equals to x minus 1 over 1 plus y at x equals to 0 is given as 1. So, I want to solve this on the interval 0 to 1 with h equals to 0.5. So, now y double prime is 1 plus y prime x over 1 plus y whole square. So, here x naught is x naught is 0, x1 is 0.5, that is 0 plus h, and x2 is 1. At the initial y at x0, that is my y0, it is 1. Now, I need to calculate y at 0.5 and y at 1 using the quadratic Taylor method. So, for doing this, what I want, I will write that y x equals to y0 plus h times y prime 0 plus h square by 2 y double prime 0. Now, y0 is given as 1. If I want to calculate y prime 0, that is y prime 0. So, from here I will calculate y prime 0, x is 0, 0 minus 1 upon 1 plus 1. So, it is minus half. Y double prime 0 will I can calculate from here. So, 1 plus y prime 0, that is minus half upon 1 plus 1. So, 1 plus 1 will become 2, square will become 4. So, 1 minus 1 upon 8. It is basically 7 upon 8. So, after putting these values here, y 0 is 1 plus h is 0.5, y prime 0 is minus 1 by 2 plus 0.5 whole square upon 2, and then y double prime 0 is 7 by 8. And after simplifying this, I will get a value 0.859375. So, this is the approximation of y at x equals to 0.5. Again, if I want to calculate y at 1, what I will use? I will use y1 plus h times y prime 1 plus h square upon 2 y double prime 1. So, I am having value of y1, which I will is 0.859375. I will calculate the value of y prime 1 from this formula after putting the value of x as 0.5 and y as this value, and then similarly I can calculate y double prime with the help of this expression, and then finally I will get this value, which is coming out something 0.9641 and so on. So, this is the overall procedure for implementing quadratic Taylor method for solving an initial value problem, and here we are getting more accuracy compared to the Euler's method without reducing the step size, means taking the larger steps. So, this is the curve of the approximate solution and the exact solution, and here you can see between 0 to 1 the curve, the two curves are quite similar, and hence we are getting a good approximation with a larger step size using the quadratic Taylor method. If we talk about Taylor methods of higher order, we can do it. The quadratic Taylor method is easily generalized to higher degrees by including more terms in the Taylor polynomial. For example, the Taylor method of degree p uses the formula y at x k plus 1 equals to y k plus h times y prime k plus h square upon 2 y double prime k and up to pth order derivative. That is, the last term will be h raised to power p upon factorial p into y k pth derivative. To advance the solution from the point x k y k to x k plus 1 y k plus 1, we will use this formula. So, just like for the quadratic method, the main challenge is to determination of the derivatives. How to determine higher order derivatives, and for that we can use the same lemma. However, we have to do a lot of computations, and hence the complexity increase quickly with the degree. It is possible to make use of software for symbolic computation to produce the derivatives of higher degree. Now, if we talk about error in quadratic Taylor method, so we can derive it in this way. So, y at x n plus h can be given by y of x n plus h times y prime x n plus h square upon 2 y double prime x n plus third and higher order derivatives. So, in this equation we will substitute y prime as f of x y x and y double prime as f 1 of x y, that is the derivative of f with respect to x and so on. So, this gives y n plus 1 equals to y n plus h times y prime n plus h square upon 2 y double prime n with initial condition y 0 equals to capital Y. Here y double prime n as you know is f at x n y n and y double prime n is f1 x n y n. So, taking the difference between 1 and 2 we get the in the left hand side it will be y n plus 1 minus y at x n plus h. So, that it will be the error in n plus 1 iteration, and let us denote it e of n plus 1 equals to, if you take the see the first term in right hand side it will be y n minus y x n. So, this I am writing E n plus h times f at x n y x n minus f x n y n plus second order term and then third and higher order terms. If we assume that both f as well as f1 are Lipschitz continuous, then we can replace these two expressions in round brackets like this one and this one by the definition of Lipschitz continuity in this way, that is E n plus 1 will be less than equals to E n plus h times k y x n minus y n. So, k is Lipschitz constant for this particular expression plus half times h square k 1 and again this term, that is basically E n, it is again E n. So, this after simplification I can write E n, if I take out 1 from here plus h k from here plus half times h square k 1 plus third and higher order terms. This expression can be written in this form. If I use the expression for the error from the first iteration, that is E naught, that is the initial error, and finally this sum can be written in this way, that is 1 plus alpha square plus up to alpha n minus 1 in this particular form, and finally it is coming out in this way. So, this particular expression gives a guarantee to be that the error will be of order h square, which is an immense improvement over Euler's method where we were having the accuracy of order h. We can also use this Taylor series for finding the approximation of a function about a given point. For example, if I want to find out the expression of f x equals to cos x about x equals to 0. So, Taylor series is given by this one, and hence I am having different order derivatives in different terms. After calculating all these at x equals to 0, so I will get 1 0 minus 1 0 1, and then substituting in expression I will get this particular 1 minus x square by factorial 2 plus x raised to power 4 upon factorial 4 and so on. So, this was about the Taylor's method, and here I told you that we can use quadratic Taylor method which is having the error of order of h square. However, we can use higher order Taylor method for getting better accuracies. Now, I will explain one more method, that is Euler's modified method, and that is just an improvement of the Euler's method which we have discussed in earlier lecture. And what is this method? Basically, in this method we will use an average slope rather than the slope at the start of the interval, like we have taken the slope at the starting point of the interval in Euler's method. So, what I will do? I will evaluate the slope at the start of the interval. I will estimate the value of the dependent variable y at the end of the interval using the Euler's method, evaluate the slope at the end of the interval, find the average slope using slope in step 1 and step 3, and compute a revised value of the dependent variable y at the end of the interval using the average slope of step h with Euler's method. So, if I want to explain this method, so basically problem is I need to solve this problem y prime equals to f of x y, y x naught equals to y naught, and I want to calculate y 1 which is the value of y at x naught plus h. So, what I have done in the Euler's method, I have used y 1 equals to y 0 plus h time f x 0 y 0, where I am approximating the value of y at x equals to x1 by the slope which I have taken at the initial point of the interval. For example, if this is the function, this is the point x naught, this is the point x1. So, here I know the value and I am taking the slope here, and I am approximating this value by this one in Euler's method. Here I have calculated this value of y1 and I will use this as the predict value. Then what I will do, I will correct this predict value by a new formula that will be y naught plus h times f of x naught y naught plus f of x1 y1 star. So, what I am doing using the Euler's method, I am finding the slope at the end point of the interval, means at this particular point, and then what I am doing, I am taking the average of the slope over the whole interval by 1 by 2 of these two. And here what I am doing, this formula I can use again and again because this is the corrector formula. And this formula I can use again and again in an implicit manner. How? You can see here I am having y1 as well as y1 star. So, I will calculate y1 from this, again I will substitute that y1 here, I will get a new y1, that is the more better approximation, and again I will repeat this process and I will get a better approximation. So, these two formulas jointly is called Euler's modified method. So, in first you need to find out a predict value of y1 and then you can correct that predict value by this formula. So, in general setting I can write this as yn plus 1 equals to yn plus h times f of xn yn. If you know the value of y n at x equals to xn and you want to calculate value at x equals to xn plus h, that is xn plus 1. So, this is predict formula and the corrector formula is yn plus 1 equals to yn plus h upon 2 f at xn yn plus f at xn plus 1 yn plus 1 star. So, if we talk about error analysis in this modified method, so suppose at starting y at x0 is given by capital Y and at each step I am having y prime n equals to f of x n yn, that is the given differential equation, and u equals to yn plus yn prime upon 2, u prime is f xn plus half. So, xn plus half is basically xn plus h by 2, I am taking the half length of the interval, comma u, and finally yn plus 1 is given as yn plus h times u prime. Then if I use the Taylor series expansion of y about x equals to xn, then I can write in this way. If I calculate y prime xn plus half, it is given by y prime xn plus half h. So, that will come in this form, and here you can note down, just look at these two terms that are similar. So, I can substitute this particular thing here. So, y xn plus 1 is given as y xn plus h time y primes xn plus half plus order of h cube. Now, the difference between y prime n and y prime at xn is given by these two functions, and we are assuming that f is Lipschitz continuous with Lipschitz constant k. So, I can write in this way, and that is equals to k times En, that is error in nth iteration. So, u minus y xn plus half can be given now by this particular equation, which is less than equals to yn plus yxn. I have taken this term and this term together, plus half h I have taken common. So, y prime n minus half h I have taken out. So, y prime xn plus order of h square. So, this is En plus half hk En plus order of h square. Similarly, I can get u prime minus y prime xn plus half, and that is given by k times 1 plus half hk into En plus order of h square. So, finally, yn plus 1 minus yxn plus 1, that is the error in n plus 1 step, is can be calculated yn plus h times u dash minus yxn minus h y prime xn plus half plus order of h cube, that is less than equals to yn minus y x at x equals to xn plus h time u prime minus y prime xn plus half plus order of h cube. So, En plus 1 will be less than En plus hk, I have taken common. So, 1 plus half kh into En, and these values I have substituting from the previous slide, which I have calculated earlier. So, if I take alpha equals to 1 plus hk plus half h square k square and so on. So, after substituting these values and writing the error in nth iteration in terms of error in initial error, that is the error in the initial iteration, then I will get this particular approximation. And again, like the quadratic Taylor method, here the algorithm has error of order h square, which is again an improvement over the simple Euler's method, that is given error of order h. So, after this we will take one example of Euler's modified method. So, example is given by this particular initial value problem. So, y prime x is 2y upon x plus x, and I need to find out the value of x in interval 1 to 1.4 by taking n equals to 4. The same time exact solution is also given for this particular differential equation, which is x square plus x square log x with natural base. And now, so here if I calculate the initial value of y at x equals to 1, it will be 1. So, y1 is 1, I need to calculate y at 1.1, y at 1.2, y at 1.3 and y at 1.4. And the same time we will compare the approximate value with the exact value, and we will see how much error we are getting in our solution. So, how to apply this method? So, the initial value problem is given as y dash equals to 2y upon x plus x, x belongs to interval 1 to 1.4. So, the true solution, analytic solution also given, that is y star x is x square plus x square log x. Now, I need to solve this problem. So, here x naught is 1. So, y naught is, from the exact solution I can calculate when x is 1, y will become 1. x1 is 1.1, y1 I need to calculate, x2 is 1.2, y2 I need to calculate, x3 is 1.3, y3 I need to calculate, and so for y4 x4, that is 1.4. So, let us first calculate y1 using the Euler's modified method. So, y1 is given as y0 plus h time f x0 y0. So, y0 is 1 plus h is 0.1 here, f of x0 y0 can be calculated from this, because it is my f of x y. So, 2 upon 1 2 plus 1 3. So, it is coming at 1.3, and this is the predict value. Now, I will correct this value. So, y1 will be y0 plus h by 2 f of x0 y0 plus f of x1 y1 star. So, y0 is 1 plus h is 0.5 upon 2, fx0 y0 is 3 plus fx and yn star will become 2 into 1.3 upon x1 is 1.1 plus 1.1. So, 1 plus, sorry, it is 0.1, 0.05 into 4.1 plus 2.6 upon 1.1. So, after simplifying this particular expression, I will calculate the value of y1, that is the value of y at x equals to 1.1. This value is coming, y at x equals to 1.1 is 1.32405, where the exact value was 1.32533. So, a very small difference we are having here, that is after third place of decimal, then y at x equals to 1.2 is 1.69982, the exact one is 1.70254, y at x equals to 1.3 is 2.12905, exact one is 2.13340, and then finally these are the approximate and exact values of y at x equals to 1.4. So, here you can note down from these two columns that the approximate solution is quite close to the exact one, and this is the implementation of the Euler's modified method for solving initial value problem. So, in this lecture we have seen two methods, those are having error of order h square, that is the quadratic Taylor method, and then Euler's modified method. In the next lecture we will learn another class of numerical methods for solving ordinary differential equation, and those methods are called Runge-Kutta method. So, thank you very much for listening this lecture.